this lesson, we are going to be focusing on learning the foundations of the periodic table, how it was developed, and some basic ways to interpret it. This information, it can be found in the Rosengarten text, Unit 2, pages 2 through 9. Now, the original periodic table is generally credited to Dmitri Mendeleev. There are others who were working on this at the same time, but this was in the 1860s that Mendeleev published his work, and what sets him apart from the other people that were also doing this work will be mentioned here in just a moment. So Mendeleev arranged the elements in order of increasing mass. So let's write that down. He arranged the elements in order of increasing mass. The reason they had to arrange this in increasing mass is atomic number. Protons weren't known at this point in time. Protons weren't discovered until 1911. So they did know relative masses, and they were able to, Mendeleev was able to put the elements in increasing mass, and he noticed that if he did that and then started a new row so that the elements in the same column, he noticed that they tended to have the same chemical properties. So what was fascinating, what sets Mendeleev apart from the others who were doing this work, is that where there was not an element that would seemingly match the properties above it and below it, he left it blank intentionally. And he was convinced that there was an element that had not yet been discovered, but when it was discovered, it was going to, the predicted properties would match for that element that was discovered. And so that's why Mendeleev's version of this work is why he generally gets the credit for this. Okay, so the key thing to remember is that Mendeleev's original periodic table was by increasing mass. And we should also note here that when elements were lined up, were lined up in columns, right, there were similar properties. And that is still true today. All right, some other terminology: periodic table, the basic arrangement, what we call a vertical column is known as a group. So any one of these vertical columns is referred to as a group. What's special about groups is that those elements in a group have similar chemical properties. Periods are the horizontal rows. And in the periodic table, there are 7 rows, which corresponds to the principal energy levels. And so that is a nice segue to talk about the periodic table and the connection to the Bohr model of the atom. Bohr model of the atom talks about electrons being in principal energy levels, which we are going to abbreviate as PELs. These are the principal energy levels are Bohr's shells. He referred to them as shells, where the electrons are located. So in this model over here, we can see that this element has 3 shells. It's got this one right here. This is n equals 1. Then we've got the second shell, n equals 2. And then this outer shell is n equals 3. So there's 3 shells, 3 principal energy levels. Atoms can have up to 7 principal energy levels. And what this does is this corresponds to the period number in the periodic table. The period number. Okay. All right, so if we go back and look at this particular model, we will see that in the first shell, there are 2 electrons. In the second shell, there are 8 electrons, and in the third shell, there are 3 electrons. So this is what we call the Bohr shell electron configuration, and it tells you that there's 2 electrons in the first shell, 8 in the second, third, and 3 electrons in the third shell. The outermost number represents the electrons that are in the valence shell. So the valence shell is the outermost PEL, right? And so this N equals 3 is the outermost valence. Valence electrons are the electrons in the outermost shell. So this example here, there are 3 valence electrons. What's special about valence electrons? They are responsible for reactivity of atoms. Now here's what's connecting all this concept of principal energy levels and valence shells. Let's bring it back to that periodic table. And it turns out that the groups are indicative of the number of valence electrons. For right now, we're going to skip this intersection because this is where the 3D electrons fill up and there's that strange overlap. So we're going to ignore that for the moment and focus on this part of the periodic table that we've been calling that the S block and the P block. But this first column has 1 valence electron. The second column has 2 valence electrons. If we go over here, this column, all the elements in that column have 3 valence electrons. And if we keep going all the way over, we're going to see that by the time we get to the noble gases, these elements will have 8 valence electrons. The exception to that, of course, is helium, which can only have 2 valence electrons because there's only room for 2 in that first shell. So let's take note of these numbers here. These are the number of valence electrons. It's very handy to know that shortcut. Each row is a shell, a principal energy level. So this first period has these elements have electrons going into the first principal energy level, the first shell, right? And so we can keep going. The second period of elements have electrons going into the second principal energy level, and so on and so forth, all the way down till we get to the 6th and the 7th PEL. And I'm just going to go ahead and write them in. All right, so there's 7 rows of the periodic table, there's 7 periods of the periodic table, and each period means that a whole new principal energy level has been added. Okay. Well, the advancement of science in 1911 with Ernest Rutherford was that protons had been discovered. And so this brings us to the modern periodic law, which talks about organizing elements based on their atomic number, not their atomic mass. So modern periodic law says that as atomic number, I'm going to underline that, as atomic number increases, the properties of elements repeat periodically. Which means with each new row. With each new row that you go down, you're going to see the properties be similar as you go down that group. All right, so that's the modern periodic law. We're going to now start talking about sizes of atoms because we want to see what those patterns are in the periodic table. Okay, so atomic radius, let's simplify this definition. Atomic radius is the measure of the size of the atom. Now the way that that's measured is you have to put 2 atoms together side by side, typically when the substance is in the solid form. We can then know how far apart the nuclei are between the 2 atoms, And if we know the distance between one nucleus of one atom to the nucleus of another atom, we can just cut that in half. So that's how it's actually measured. But conceptually, the atomic radius is a measure of how big it is. Okay. So what we are going to do is we are going to consult reference table S, and we are going to find atomic radius. The atomic radius is listed in picometers, and we're going to look up the atomic radii for these various elements. But specifically, we are going to just look up period 3, which is this row, and we're going to do this for group 2, which is this column. And when we do that, when we consult this, so this is atomic number 4. If I go to atomic number 4, I'm going to see that that's beryllium. I read all the way over. The atomic radius is 99 picometers. Okay. So if I do that and go ahead and look up all the atomic radii for all the elements by using reference table S, I'm going to see that the numbers change. 140 for magnesium. And as we go down this column, it's going to go to 174 and 190, and then 206, and then 211. And again, this data is all found in reference table S by looking up the atomic radii. Let's continue on for period 3. If I look up period 3, I have 160, and then we already had 140 listed. Let's go over here to 124, then 114, 109, 104, 100, and 101. Okay, so what we are seeing here, generally speaking, let's take a look as we go down this group, right? Going down this group, we see that the atomic radii get bigger. So let's write that down, right? So going down a group, atomic radius increases. And if we are asking ourselves why, well, think about this. As you are increasing this radius, as you're going down, there's a whole new period. There's a whole new principal energy level that's being added, right? So you're going from one principal energy level to a second principal energy level to a third as you go down. So there's more PELs, plain and simple. There's more principal energy levels. So therefore, yeah, there's just a whole new layer of electrons that are being added. But what gets difficult to wrap your head around is as you go left to right, the atoms are getting heavier, right? There's more protons, more neutrons, more electrons. So why, if there's more of all those subatomic particles, why does the atom apparently shrink? Well, let's start by writing this down. So going across a period, the atomic radius decreases. And the question is why? And we're going to talk about this as if it has two parts. Number one, we are agreed that as you go left to right, there is one more proton in the nucleus. Okay, so let's start by talking about that. So number one, there is what we say an increased nuclear charge. All that really means is that there's more protons. And what that really means is that the nucleus is more positive, more positively charged. So you can think about this as you go left to right within the period, the nucleus is getting more powerful. It's getting more powerful. Okay. The second part of this is that the added electrons, when we add them, they're not going into a new principal energy level. They are going into the same principal energy level. Okay. So as we add protons, that nucleus is getting more and more powerful, and we're adding more electrons, so the valence shell is getting more and more negative. That increased positive and that increased negative within that same shell means that the atom will actually shrink, that the atom sizes shrink. as the protons attract the electrons. Okay. This graphic right here is meant to give you a visual to help you remember this. As you go down the periodic table, atoms get bigger, so it kind of looks like a snowman. As you go left to right, that snowman still exists, but the snow is melting, right? So the snowmen are shrinking in size, but nonetheless, they are still getting bigger as you go down each column, right? So this, if you can understand atomic radius and why this is happening, this is going to really help you as we move forward with other topics. So we're going to finish off this particular video with talking about element types, metals, nonmetals, and metalloids. Right? You've kind of already looked at this already, but we're just kind of formalizing this with notes. So we're going to start by identifying the metalloids. So start in this corner, this upper left corner, shade that in, and then you're going to shade in 4 elements going down into the right. And then you're going to shade in this element and this element, right? And so, but not this one, because this is aluminum, and aluminum is very much a metal. Okay, but these elements right here are what we call the metalloids. Sometimes they are referred to as the semi-metals. These elements here are the nonmetals, but don't be fooled, there's one more nonmetal over here, and that's, of course, hydrogen. And then everybody else are the metals. All right, this is where we're going to take a break from this particular set of notes. We'll be continuing this lesson on in the next video, but otherwise I will see you back in the classroom.